Hello student, in this video I'm going to discuss about a topic that is about similarity. We have discussed an example in the last video showing the significance of similarity measurements. So today I would like to introduce about what is similarity and how we can measure that similarity. So you can see in this picture, both pictures look like similar but not similar. The quality or state of being similar, likeness, resemblance as a similarity of features. That is from the dictionary. That is literal meaning. Or we can say that similarity, it's like we know it when we see it. That is why it is defined. It is hard to define. The real meaning of similarity is philosophical question. We will take more pragmatic approach. So we shall talk of measuring similarity now. However, we are usually measuring dissimilarity. So try to understand this concept. Whenever we try to measure any similarity of two object, then actually also we are trying to measure the dissimilarity. Similarity means the larger the number, the more alike two objects are. Similarity value, if the value of the similarity is larger, then we can say that those two objects are more alike. If the large, if the dissimilarity value is larger, then we can say that the less alike two objects are. And here to measure that similarity and dissimilarity, we use distance. So distance is a common synonym of dissimilarity. So we may speak of distance measure and dissimilarity measure interchangeably. So whenever we talk about similarity, we can talk about distance measure, because distance measure can give you the dissimilarity value, and whenever the distance is larger, then we can say that the objects are not alike. So however, a distance measure is not the same thing as distance metric. We will say why later. Here you can see similarity queries are often expressed as nearest neighbor queries or range queries. Suppose there are two queries A, B, three queries A, B, C. So what is the nearest item to the green item? So we need to find what is the nearest item to this green item. So and can be generalized to the k nearest neighbors. So we'll try to understand what is nearest neighbor in later part of this topic. And what items are within R radius of blue item. So again, if we want to try to see what items are within R of the blue item, within radius of the blue item, R is given by the user, radius will be given by the user. So this type of thing can be expressed in terms of similarity queries. In order to better appreciate and evaluate example given in the every part of this talk, will now introduce dendrogram. Terminal branch, root, internal node, internal branch, leaf node. Okay, the similarity between two objects in a dendrogram is represented as height of the lowest internal node they share. Here you can see these two objects share the same height. That is why those are sharing the same node. Okay, that the internal node. And this object height is not equal or similar to the rest of them. So that is why it is separated out in the root phase. The similarity between two objects in a dendrogram is represented as the height of the lowest internal node they share. Again, here you can see this is another dendrogram. The similarity of this human being with the chimpanzee and other pre-successor, how they are similar and how they are dissimilar with cow. So we can see this dendrogram as a measurement of the similarity between a human being and with any animal being. How much we go far, then those things are dissimilar in that way. Okay. Here you can see this is a eurogram. It might be eurogram, it might be dendrogram. It depends on how we draw that. This is human and chimpanzee, and same structure actually as like the dendrogram. Or you can use the tree diagram, or you can use clado diagram, Fano diagram. So these are different types of diagram to describe the same concept. Okay, so human is more similar to a chimpanzee than the gorilla, than the orang, than the gibbon, than the bovine. So why measure similarity? Classification is a very important field to decide or to think about this similarity. Given an unlabeled, suppose there is an item Q which is unlabeled, means we don't know anything about Q or any class about Q. So we need to assign it to one of the two or more predefined classes. Suppose we need to define the class of Q one or two or more predefined classes. One of two or more predefined classes. So we can do classification without measuring similarity, but similarity based methods are very competitive. Here what it says that we can do classification without measuring the similarity also, but using similarity methods we can put more understandable facts, and it's very competitive. Clustering. Find natural groupings of items under some similarity measurements. Indexing. Given a query object Q and some similarity measure, find the nearest matching item in the database without having to examine every item. So that is another concept of similarity measurement while we try to indexing an item in a database. So definition, distance measure. Suppose let O1 and O2 be two objects from the universe of possible objects. The distance, here we are talking about dissimilarity. When we talk about distance, then we are talking about dissimilarity. Between O1 and O2 is a real number. That should be. That is very important point. Denoted by d of O1 and O2. It is a function of this distance function O1 and O2. So like here you can see, this is one text Peter, this is also one text Peter. So how they are similar? Suppose again this is chimpanzee and this is gorilla, and how they are similar? This is 0.23 more similar, because the distance is lesser, this similar value is lesser, so we can say similarity higher. Here you can see these two fingerprint has higher dissimilarity value, means, or you can say higher distance value, then we can say those objects are not alike. Like that way we can say how things are alike or not alike using the distance value. When we speak inside one of these black boxes, we see some functions on two variables. These functions might vary simple or very complex. In either case, it is necessary to ask what properties should these functions have. Obviously, here also to find out the similarity between Peter and Piotr, we try to use some functions here. So this act like a black box. So this might be simple also, this might be complex also. But in either case, it is necessary to ask what properties this black box or these functions have. So what properties should a distance measures have? That is need to be understand here. You can see the properties of this DAB always be equal to DBA, means distance. Any distance measure should have this property, means D of AB should be equal to D of BA, and D of AA means same object, then it will be 0, constancy of similarity. DAB equal to 0 if and only if A equal to B. DAB less than DAC plus DBC, triangular inequality. What it means? What is triangular inequality? Here, why is triangular inequality so important? Virtually all techniques to do index data require the triangular inequality whole. Here you can see object A, B and C. Suppose I am looking for the closest point to Q in a database of 3 objects. Objects are these and Q is the query. So we need to find out which one is closest to the Q. Further, suppose that triangular inequality holds and that we have compile a table of distance between all the items in the database. Suppose we have compiled this distance table from database. If I find A and calculate that it has 2 units from Q, it becomes my base so far. If I find B and calculate that it is 7.81 units away from Q, then I do not have to calculate distance from Q to C. Why? Why? We have said that A is nearer to B, nearer to Q than B, because to B the distance is 7.81 and to A is 2. That is why we can say that A is nearer to B, and we need not to check the C, because why? Why we don't need to check the C? D of QB, suppose D of QB, distance of QB, it should be always less than or equal to D of QC. Why? Because D of QC plus D of BC, D of QC plus D of BC is always greater than this, because this is triangle, because this is a triangle, and we know that summation of any two edges will be always greater than the third edge. So that is why this is the triangle inequality. This is the triangle, and we know that is why from triangle inequality we have to say that distance of QB should be always less than summation of distance of QC and distance of BC. So here you can see 7.81 distance and 2.30, that value come here. Okay, so 5.51 less than equal to D of QC. So I know that C is at least 5.51 units away, but my base so far is always 2. So we do not need to check C, because we have already find 2. But if the value is lesser than 2, then obviously we have to choose C. So that is triangle inequality, and is very important in case of similarity measurement. Here you can see sometimes the triangle inequality requirement maps nicely onto human intuition. Consider the similarity between the horse, zebra and the lion. The horse and zebra are very similar and both are very unlike the lion. So that is about triangular inequality. Again, we can see here sometimes the triangular inequality requirement fails to map into human intuition. Here you can see consider the similarity between the horse, a man, and the cantor. The horse and the man are very different, but both share many features with the cantor. This relationship does not obey the triangular inequality. So that also a flaw in this triangular inequality. So what other properties should we require of a distance measure? It should really measure similarity. It should be fast to compute. Obviously, here one thing you can see here, Euclidean distance and Hamming distance has the complexity O of n, and dynamic time wrapping and string edit distance are O of n squared. So point is that any distance measure functions need to be faster, otherwise it will take too much of time. Here complexity of this Euclidean distance and Hamming distance is O of n, and complexity of dynamic time wrapping is O of n squared. So that should be always lesser. So we should not create any distance measure functions which is greater than this, or which is more taking more time while calculating. It should be space efficient. This is usually not as important as time efficiency, but we may also look into this. Look into this. It should allow indexing. If the measure is metric, this is automatically true. Otherwise, it depends. So whenever you try to design and distance measure functions, if that provides you a matrix, measurement in a matrix, then it is already indexing. Otherwise, it will depend upon whatever measure you choose. A first lower bound measure is desirable. So a first lower bound measure is desirable. So suppose if not first to compute, a first lower bound measure is desirable. Why? Suppose here you can see lower bounding sequence. Assume that true distance AB is the correct distance function, but it's very expensive to compute. And that lower bound distance AB is a cheap lower bounding estimates of true distance. The above algorithm will allow faster sequence searching. So sometimes what happens is that to find the actual distance between AB might take time, but to find the lower bound distance between AB might take lesser time. So having that also will suffice our need. We don't need to go for true distance calculation. So that is one point. That is why it is mentioning the first lower bound measure desirable if your distance measure function is taking some time to compute. True distance computation. If we want to measure the similarity between items, we will have to measure some features, obviously. Just like yesterday, in last video, we have talked about that. We have to measure some features. It might be binary, it might be nominal. Only two possible sets are possible in case of binary: true, false, Jew, Gentile, married, unmarried, or nominal generalization of binary to three or more states: Jew, Catholic, Protestants, married, divorced, widower. In basketball, jersey numbers are nominal. You cannot order or do any mathematical operation on nominal data. So in those kind of scenario where the things are nominal, you cannot order them. So or you cannot do any mathematical operation on nominal data. And ordinal, same as nominal, but order matters. However, the distance between two values is not meaningful. So here you can see some values, some variable can be in ordinal also, interval also, so ratio also. So all these variable can be, all features can be in this type of categories. So consider color. What kind of feature is this? Nominal color will be like blue, red, yellow, etc. Ordinal discrete will be red, orange, yellow, green, blue, indigo, violet. And also ordinal continuous like be the values of the spectrum. Factor continuous would be like this: red, green, blue, or hue, saturation, luminosity. So that color feature can be expressed in various attributes or various values, and that depends upon you. We sometimes have a choice of representation. Often making the right choice can be very important. So here you can see the similarity between two items depends on the features we measure and the distance measured itself. So here you can see last name similarity. It can also happen. Last name similarity might be there, which is 0 means these are similar, but skin color similarity is not similar. So that is why what type of feature you are going to measure or how you are going to measure, that is very, very important. Sometimes we are given the perfect features to measure similarity. Sometimes we need to. So it is upon you. Generate features. Suppose we hope to find similar people with regard to their medical conditions. Knowing both their height and weight is not helpful. Knowing their BMI is. So that is why BMI is important in this case. If we want to check the medical condition. Sometimes also our features may contain noise or outliers, so we need to clean the features. Sometimes we may need to transform the features to create the normalized features. Sometimes also we need to reduce the features because there might contain lots of numbers of features which might not be adequate or important enough to calculate the measures, similarity measures. So we might need to reduce those features. And also there is no single magic black box for measuring similarity. However, there are two useful and general tricks like feature projection and edit distance. Project the data into feature space. The distance in the feature space becomes the similarity. That can be a process. Transform one object into another. The cost of this transformation becomes the similarity. So that also a process. So these are two tricks because there is no single magic black box for measuring similarity. So we can do or you can opt different techniques to do that. Here you can see, suppose we want to project these objects or you can say birds in this feature space. So here you can see from left to right: bee, hummingbird, Costa's hummingbird, ruby topaz hummingbird, kestrel, giraffe falcon, bald eagle. Those are placed in this here according to body mass, according to ratio of beak length over body length. So use of features to project the items into feature space. The distance between two objects in this space is measure of dissimilarity. In that way we can measure the similarity of any two parts. So here it is important to note that what are the features we are projecting in the feature space. On this is two-dimensional feature space, that is why we are putting only this ratio of beak length over body length to the body mass. We might put another features also, but that might not give you exact similarity value. So that is also important matter to think about. Here again, feature projection example 2, that is feature iris data. You can find this dataset everywhere in internet. 3 variation of iris exist in the datasets, 50 of each, 50 values, 50 samples of 3 variation of iris flower are there in the dataset. This is iris setosa, this is iris versicolor, this is iris virginica. So we can plot those dataset in a diagram using the petal length and petal width. So in that way you can see the similarity between any two iris flower. Again, a generic technique for measuring similarity, to measure the similarity between two objects, transform one object into other and measure how much effort it took. The measure of effort becomes a distance measure. It is possible to transform any string Q into string C using only substitution, insertion and deletion, and assume that each of these operators has a cost associated with it. The similarity between two strings can be defined as the cost of the CPS transformation from Q to C. So here another edit distance example, we can make two time series appear more similar by making one point on one map onto 2 points into the other. For example, suppose we have 5, 6, 8, 8, 7 and 5, 6, 8, 7. At 1 to 1 measure we would have to match 8 into Q to A, 6 in C, 5, 5, 6, 6, 8, 6, 8, 8, 7, 7. But however, if we allow nonlinear alignments, very number can match with itself, like 5, 5, 6, 6 and 6, 6, 8, 8, 8, 8, 7. Like that way, another way of looking at it is an attempt to make the two subsequences more similar by inserting values. So we can insert values here rather than we are matching or nonlinear alignments. So in that way you can see this is dynamic wrapping to create or to find the similarity. So this inclusion might create or understand you that how they are similar. So this is called dynamic time wrapping, but it takes time, O n square. So here you can see fixed time axis and wrap time axis. Nonlinear alignments are possible, but in fixed time axis sequences are aligned into one. So here you can see in case of fixed time axis, these two things are similar, but these two things are not similar with this one. But as a whole, intuitively, as you can see, this graph might be more similar to this one than this one. So that is why using dynamic time wrapping we can say that this tree graph is more similar than this one. That is why you can see in this Zando graph this is totally separate out from this branch. So we can use dynamic time wrapping also. Again, there is another metric, that is Minkowski metric. Here you can see how we can use that. Here P1, P equal to 1 for Manhattan distance, P equal to 2 for Euclidean distance, P will be infinity for max, supermum, or you can say sub. Here DQC is any two objects, and we will try to understand the distance between two objects and we will try to take the root over it. Then P value will be 1 when we are taking the distance as a Manhattan, and P value will be 2 when we take that distance as a Euclidean. So we have projected our object into feature space. How do we measure the distance between points? So we can use these 2 points. So suppose we have database of 3 items with 2 features, some number of children and temperatures. Number, children, temperature. We want to know who is the most similar to Mr. Red under the Euclidean distance. So who is more similar, this one or this one? So it will try to find the distance. So Minkowski metric is sensitive to the units we use to measure features. A very undesirable property since the units are usually arbitrary. To solutions suggest themselves, normalize the features or use a weighted version of the Minkowski metric. So we can vary the Minkowski metric. But thing is that in any way we can use different type of distance measure metrics to find the similarity. Or also we can do the normalizing thing for more better finding the similarity values. So here one weight is used to create more good similarity value measurements. Further, assume that W is a factor containing the relative importance of the features. So if the feature is more important, suppose here 2 points, Celsius and Fahrenheit. So which some features might be more important, then you can give some weight here, which will increase the distance or similarity value. Minkowski metric have a simple geometric interpretation. Like if it is Euclidean, we can use this radius or circular notation because the distance will be calculated in a circular frame. But in case of weighted Euclidean, it will be a oval shape. But in case of Manhattan, it will be a square shape. But in case of Max, it will be a diamond shape. So Minkowski metrics have simple geometric interpretation. So we can understand how the distance varies in case of different metrics or different geometric interpretation. In case of Euclidean, the distance will be measured in that way, circular fashion. But in case of weighted Euclidean, it will be measured like a oval shape, like that way. So that is all about. Next, in this slide, actually clustering is included, but we will discuss clustering later. But before that, before clustering, we will try to introduce about nearest neighbor measurements in the next video. And whatever I have discussed in this video, try to go through it. If you find anything tough, let me know. We'll try to resolve it over Google Meet. Thank you.